Hello everyone and welcome to Handmade Hero, the show where we code a complete game live on stream. I believe we had slight technical difficulties this morning. I had to reboot the machine as I sometimes do. For whatever reason, the OBS arrow capture thing that we use to stream, every couple of weeks it just goes black. Like it doesn't show anything but just a black screen. And then I have to reboot the machine. There's no other way to get it to come back for whatever reason. I don't know if it's a problem with Windows is no longer outputting the arrow compositor information anymore for some reason, or if it's a bug in OBS. I have no idea. But we are okay now, and I believe I've got the day right, day 364. I had to reset my little day counter as I have to. There's day 363, so day 364 is correct. So we are good to go now, and we can go work on our program, which is what we want to do. So let's go ahead and get started here. We are, and I should probably also get our Blackboard back, because obviously since I rebooted everything, got shut down. There we go. Close that. And open up Handmade Proj. There we go. So where we left off last week is we had finished all of the 3D pipeline stuff necessary to make it so that we're actually properly rendering in 3D now, with actual transforms and all that sort of stuff. So, you know, we can actually zoom and rotate our game around and that sort of stuff, which is nice. So this is what I wanted for being able to see things in debug mode. And we can now proceed with putting in our Z buffer. So we've got a lot of options for this, actually. You can see, so right now, we're not doing any sorting at all. That's where this flashing is coming from. These sprites are literally right on top of each other at exactly the same depth as well. So I don't think even a Z buffer, if we turned it on right now, would do anything for that. You can see what's sort of happening is that, hey, whatever order we happen to submit them, that's how they get drawn, so there's really no rhyme or reason to it. For the most part, well, there is, but it's a very unintentional sort of random rhyme or reason, you might say. Yeah, that's the situation as it stands. And so our goal, I can walk the hero around in this weird sort of flattened state. It's rather amusing, actually. Look at him go. All right. So what we want to do here is we want to start doing the thing that we did all this 3D work to do in the first place, which is switch to a sorting scheme that actually uses the Z buffer and doesn't have to go through a individual object-to-object sort, which is what we had implemented and which I wasn't particularly happy about. Okay. So we need to be able to do that, and if you take a look at what's going on here, you can kind of see that right now everything is just a flat sprite on the Z. It has no Z depth at all in terms of changes, right? So if you look at everything's completely flat in Z. So everything has its X, Y position as it used to, but it has no Z at all. It's just everything is just a thin plane with nothing rising up out of it at all. And so the first thing we're going to have to think about is how we actually want to submit things so that they have a sensible version of sorting that will work with the depth buffer. And so let's just talk about that for a second, because that's like the next logical step we have to do to turn on the depth buffer. Now, obviously, we can just turn on the depth buffer. The only thing we have to do there is map our Z range to something useful. Which, you know, obviously we have to do with our perspective matrix, has to map our Z range to something useful, because our Z is will be used for the Z buffer or the depth buffer, and turn it on. But other than that, the rest of the finesse in getting the game to work properly in terms of sorting is to figure out how we should send down the sprite information so that the Z buffer does what we want it to do, right? Because right now, that would not happen. Right now, we're sending everything down flattened on top of itself. It's not going to do any good. So what we will probably do, I'm guessing, is we'll go with kind of a standard trick one that I've seen done before. I don't know who was the first person to think of this or use it in a shipping title or anything, but I've seen it done a lot. And that is to say, well, okay, essentially we've got this flat plane here. And that flat plane is going to be fine for doing some things. Like if I want to put ground chunks on here, or ground tiles or whatever, anything that's on the ground is going to be okay in terms of sorting because it's all just part of the ground. It's at the same height in Z and nothing confusing is happening. And even if I wanted to put something kind of over the top of something, I could just give it a slightly higher Z value, just a little bit higher, and then it would work properly, right? I can use the Z values to sort of stack things up on top of each other just a little bit if I want to. And what I could also do, if I need to, is I could use the same Z value for them and just send them down in sorted order as well, if I wanted to, right? Because typically these things wouldn't be moving up and down past each other, so I would know that things that stack on top of each other, how they should stack, right? I could do that as well and just use a depth comparison function that was like greater than or equal to in Z, for example. Well, I guess in this case, it'd be less than or equal to because the Z direction will be flipping. Although we can really control that, but that's beside the point. Anyway, so if you think about what's going on there, it's like, well, stuff on the ground isn't really the problem. So the problem for us comes when we've got like these trees or the hero or whatever who's sort of supposed to be standing upright, And the problem, what's going on there, is that things that are standing upright have to occlude each other properly when they stack, right? So, if I've got a tree and I was to draw it here, I could make sure that it drew on top of the ground. But then if someone was standing behind it, how do I make sure that they appear behind the tree? Or if they're standing in front of it, that they appear in front of the tree, right? And so what people often will do is if we look at this side on, if the camera is looking down this way, they'll sort of put the sprites like this, right? They'll sort of stack them so that they do go upwards in Z. They just go upwards at the same angle as the camera comes down, so they appear nice and flat onto the camera, but they, get kind of taller as they go. So that part actually may be harder for us because we're not going to be very oblique with the artwork, depending on the circumstances. So having it face directly at the camera may also not quite be enough because the actual facing direction for the camera may be something more like this in terms of what we're actually thinking of in terms of there may be very little tilt there. But the scheme still works because if you think about it, what we can do is still produce the sprite that will look roughly correct, but that does have this shape, even for a different down look, right? And what I mean by that is you can imagine, let's suppose that I'm looking down like this. And so in order for a sprite to appear its correct size on the screen, it would have to be placed like that, right? Well, it's free for me to do the same thing with the sprite, meaning if I come down like, if I think about how this is getting projected, right? If I have my screen, this is not a very good diagram, but if I've got my screen here, right? If I imagine the projection and say, well, I want the sprite to appear as if it looked like that on the surface of the monitor, if I want to, I can extend this line further down, right? And instead send down that sprite. And that sprite has the same appearance on the screen as this sprite does, right? But this one stacks much more cleanly with someone who might be in front of it. What do I mean by that? Well, imagine I have, something that's coming through here, and I want it to appear in front of this guy, but I'm drawing him like this. Well, it'll appear behind incorrectly in that case, Whereas if it looks like this, it will appear correctly. Why is that? Because this is sort of the ground point of the sprite. Like if we think about what we see when we look at the sprite on the screen, here's the tree. This part, our brain, because it is a tree, even though it's just a 2D flat thing, our brain immediately goes, oh, this part is low to the ground. This part is high to the ground, right? That's what your brain is thinking. So matching the sprite, right, so that this part is actually low in Z and this part is actually high in Z, leads to what the brain will perceive as correct sorting results when something of mid-height comes through here, right, and it's looking like this as well. It stacks properly against this thing, whereas if they were like this, it wouldn't, because the difference in Z is simply not enough to capture the fact that the ground is down here, right? So what we want to do is probably output our sprites so that we do a tracer down to the ground where the sprite is sitting. So we have the ground point, and we know we're here on the monitor plane, right? We probably want to do a tracer and then say, okay, we then want to go up on a diagonal that's at a particular slope, and that slope we'll have to select sort of to be something fairly eccentric like that, something fairly, at a high angle, I guess is what I'd say. This is probably going to be more than 90, right? We want that to basically be prescribed and say, all right, let's generate a sprite where we go up to this particular point so that we end up with the correct width on the screen, or I guess I should say the correct height on the screen for the sprite that we prescribed for the bitmap, right? Because we've got an idea of H and W for the bitmap, and we want the screen sort of idea of height to be correct so the aspect ratio of the sprite is maintained, but we want it to slant upwards relatively dramatically there so that we get that better sorting, right? So that's what we kind of want to do here. At least I think that's what we want to do here. It's hard to say, but I think that's probably the best option. And so what we want to do is make it so that, you know, from the top down, our thing does look like, okay, there's some trees here, you know, and there's a hero or whatever, and, you know, maybe there's a tree in front of the hero and stuff like that. But from the side, right, if we were to look side on, these trees actually look like that down here, you know, and this tree looks like that here, and the hero looks like two sprites, one that's there and one that's there. You know what I'm saying? So we kind of want to do something like that because the effect of pushing those sprites through the Z buffer will give us what we want. And that's, I think that's basically, that's the basic idea anyway. Yeah. So I think that's what we want. I think that's going to be better than trying to use flat stacked things. Flat stack things, I think, would get us right back into the problem of how do we sort these things. So I think we want things to be slanted so that they will stack on each other naturally and use the Z buffer properly to figure out who is standing in front of whom. Okay. So that's kind of what we need to do, and hopefully now that you've seen that, you understand why I think this is going to be important for us for debugging, the ability to tilt down like this, because essentially we've got to create these sort of three-dimensional placards, and without being able to bend the camera, we're not going to have very much intuition for how we actually created them. We're going to write some code and hope that it's right via inspection, but you know, without being able to actually play around with it and see it like I can when I do this, we wouldn't really know that we'd gotten it right, or more importantly, when it looks like we'd gotten it wrong, we wouldn't have a lot of intuition as to why it was wrong. It might look relatively correct in 2D, but then when we spin it in 3D, we go, oh, right, okay, it's totally busted here, right? So that's what I would say, and so that's what I'm going to try and do here. So let's start, I guess, by talking about how to turn on the Z buffer. That's probably the first thing that we want to do. And again, we've already talked way back at the beginning of this set, if you want to go back and double check what a Z buffer or depth buffer is. So hopefully that's something that you have familiar. If you don't, if you're not familiar with that, I'm not going to re-explain it. Go check that one of those previous versions where I talk about it in depth. I think there's one episode in particular where I go through it and talk about how it works entirely. So that's the one to check out. Maybe it's about six episodes ago or 8 episodes ago. I don't remember. It was at the very beginning. So probably a little more than that, actually. Anyway, so if I go into our OpenGL pipeline, I'm just going to show you roughly where this sort of thing comes into play. So you can see our OpenGL render commands here. And you can see us doing our, our texture 2D, scissor test, blend, etc. What we need to do here, and I don't think we ever disabled it because it's not on by default. So you can see, yeah, we're not really ever doing anything to disable it. It's something you have to turn on. And so in here, I want to be able to do a thing where I say GL enable. And what this is called, I guess in this case, let's see. I don't care about that. What I want is OpenGL render commands. There we go. When I'm enabling things such as texturing, I want to be able to enable depth test, right? GL enable GL depth test is the thing that says turn on the depth buffer. And when I say turn on the depth buffer, I actually mean testing against the depth buffer. There's actually 2 separately controllable things you can do with the depth buffer in the fixed function pipeline. One is to control whether or not you are reading and testing from the depth buffer. The other one is to control whether or not you are writing to the depth buffer. And so there's actually also another one called GL depth mask. And I'll show you this one in docs.gl because it's not an enable call. It's its own call. And you can see here what happens is it's sort of a separate enable kind of thing. I don't know why these don't go through enable. But basically, GL depth mask is the equivalent of another function I don't think we ever talked about, GL color mask, where you can set the red, green, blue, and alpha channels. And what these do is they essentially allow us to control what we're working with, right? So if you imagine the default state, we don't have to set these, but the default state looks like this, I believe, which is that every channel gets written to. Depth, red, green, blue, and alpha are all the things we can write to except for stencil, which we haven't really done anything with, but you can see that one has one down here as well. We don't need that at the moment. So all the things that we're writing to would be enabled in this case. Now what's important to understand about this, and this is true in the fixed function pipeline, it's also true if you move to shaders, you have even more control there. But what happens here is you can see this allows me to control what I'm actually writing to as well as what I'm testing against. So I can say whether or not I'm testing against the depth buffer for occlusion, but I can also say whether I'm writing to it or whether I'm writing to color channels as well. What that means is if I wanted to, I could write only to the depth buffer on a pass if I wanted to, right? And that's important too because it means you can build up depth buffers without drawing anything, which sometimes becomes important. Something that's very common in rendering is called a depth prepass. And so, things like that are only possible because you can change what you're writing to at any given time. Yawning. It's tired in here. You can change what you're writing to at any given time and decide not to write colors. So you can just write depth if that's what you want, and vice versa. You can choose not to write to the depth buffer, only read from it, for example, and write colors, et cetera, et cetera. But basically, if taken together, this sets up the entire drawing situation that we're working with. Now, there is one caveat here, which I can look up at the frame buffer. I don't know where we allocate frame buffers. Probably right here. GL by frame buffer. So You can see what happens here, GL frame buffer texture 2D, where we put a texture attachment into one of these frame buffers. One of the things that we're going to have to deal with, and I'll just put the to do in here, to do create a depth buffer for this frame buffer. One of the things that you have to do now, in addition to enabling it, is if you ever change the render target, because your default render target comes from a different place, and we'll talk about that in a second, but anytime you create a render target like we were doing here, that render target cannot use depth buffering if it doesn't have a depth buffer. And you can see here that when we bound this frame buffer, the only thing that we gave it was a frame buffer texture, which is basically saying a color to write into. We never bound a depth buffer. Now, binding a depth buffer is very easy to do, so it's not a big deal. It's just a call that looks exactly the same. It looks like that. So instead of saying that it goes into a color attachment, you can say it goes into a depth attachment, and then you can use depth buffering on that frame buffer. But we have to actually generate a texture for it, which at the moment we are not doing. So that's really all that is. And this will be something we'll have to deal with when we go and re-enable sort of like the room stacking or stuff like that that we had wanted to do. So that's it for depth buffers. There's not a lot to it. However, like I said, we do need our default buffer to have depth information in it. And so there is one other thing we have to do, because remember that, and you remember we did this when we looked at the sRGB stuff, our original color and depth buffer and everything else comes from OpenGL's Windows initialization stuff in Wiggle. When we actually do our Wiggle setup for set pixel format, when you look in here, you can see that we've set up a bunch of attrib stuff and all this sort of thing, right? Where we go like suggested pixel format, intended pick, and we've got double buffer and support OpenGL ARB and all this sort of stuff in here, pixel type, RGBA ARB, and that sort of thing, right? And what you can see here is, like, for example, in both of our things, we are nowhere specifying whether we wanted a depth buffer or not, right? And this is important. So if we take a look back at some of this code that we had done when we did it without thinking we would want a depth buffer, if I go to pixel format descriptor here in Windows, where is it? There it is. You can see that there's a C depth bits, like a parameter for that very piece of information, right? And so if C depth bits isn't set to something, we wouldn't be guaranteed that we would get any kind of depth buffer at all, right? It could just not give us one. And so it depends on what kind we want here, if we want a floating point depth buffer or not, or exactly what we want. I don't know how greedy you can be in this case in terms of backwards compatibility. So, one thing for C depth bits might be to say 24, and to say that there'd be 8 bits of stencil in there, probably, something like that. And if you want to be greedy, you could say 32 and say I want a full floating point depth buffer. We probably don't need that, so I think for backwards compatibility's sake, asking for a 24-bit depth buffer is probably the safest thing to do, because it probably would extend to most platforms that I know of that someone could reasonably be putting Handmade Hero on. But that's only our path for failing the extended pick, if that makes sense. So, when we come back here to this guy, this one doesn't really talk about those at all, right? It does that suggested pixel format index extended pick thing through wiggle choose pixel format ARB. I don't remember if you have to set something here in addition to pixel type ARB that says whether I want a depth buffer or not. So probably what we're going to have to do is take a look at wiggle choose pixel format ARB and see where's the spec? Hello, specification. All right, folks, there is a specification to this. I don't care about any of these things. I want the spec, please. That'll do. Here we go. And so in this case, yeah, you can see, so we're not specifying any of these. We're not specifying red bits, green bits, blue bits, or alpha bits, and we're not specifying depth bits. I don't know if that's because we were smart or not. Let's take a look. So I don't know why we weren't specifying these. I guess because we didn't care. But we need to tell it that we at least want a depth buffer. And I don't know if there's any particular way to fix that. So these are minimums, so I guess that's fine. Because that way we wouldn't prevent it from giving us a 16-bit color buffer if it had one, right? So that seems reasonable. So I could do red, green, blue, alpha, and depth, and just specify those. And that seems good, right? We're knocking out number 10, which is 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, yeah. So we're knocking that one out and ending the list there. So that means we would need to sort of put these up here. All right. So red bits arb, we'll say 8. Green bits arb, 8 again. Blue bits arb, alpha bits arb, and depth bits arb. So now we should be able to say knockout number 20 if we're not going to specify that if it doesn't support sRGB. And in theory now we should be specifying in both cases the information we need to specify in order to get those buffers. Now we do need these values, so we need, you know, red bits, green bits, blue bits, alpha bits, and depth bits. And so now in theory we should have a functioning depth buffer, right? In theory. And by the fact that we're not seeing anything on the screen, I believe that indicates that we did in fact turn it on. Because remember, our projection matrix is not actually, our projection matrix is not actually doing anything with the z. So yeah, you can see here if I leave it off, it draws. If I enable it, it doesn't draw, right? So I believe that is actually turning it on correctly and that we do have one. Now, a couple other things that we're going to have to do. So first of all, we need a GL clear because one of the things that would prevent us from seeing anything on the screen is the depth buffer, don't forget, is an actual buffer that needs to be cleared, right? It's actual information, just like color information. It just stores the z values of the things at the locations of every pixel. But right now, we're only clearing the color buffer bit, and we need to clear the depth buffer bit as well. Or I shouldn't say, we're only clearing the color buffer. This color buffer bit says clear the color buffer. The depth buffer bit says clear the depth buffer. The bit part just means it's a bit mask that I OR together to tell clear what to do. And I can also, much like GL clear color, I can also say what I want to clear that value to, right? Clear depth, there it is. Oops. Ah, web browser. There we go. So you can see here, clear depth, it gives a depth value here that we're going to clear to. And 1 is considered the furthest away. So again, z gets larger as you get away from the camera. So if I wanted to, I could also say, hey, let's just specify this explicitly that we're going to clear to 1. So now we're saying clear to this RGB and A, and also clear to this depth when you go. Now this will become important potentially later, because remember, if we want to, we can do a number of things here. I don't think we'll actually need to use this, but we can use that depth clear to create slices through the image as well, right? If everything compares against the depth buffer, if we wanted to make sure that we didn't draw anything past a certain point, we could clear the depth buffer to that point, and then nothing would compare in front of it, and we would never draw anything behind it. So in effect, this is a clipping plane in and of itself. So in addition to setting the near and far clip planes, for example, we also have the ability to set a third kind of value. Not that we need it for anything, but you can with that. Just for the record. All right. So now that we're clearing the depth buffer, I would suspect, yeah, there we go. Now that we're clearing the depth buffer, we're getting a sort of z-tested drawing here, but it's still completely not what we want for obvious reasons. And I guess I'm a little confused at what I'm seeing. To be honest, this isn't exactly what I would have expected. I'm not sure why we're getting those gray outlined areas. Oh, wait, no, I do know. All right, so I know exactly why those are, in fact. And we can actually fix those earlier rather than later, so we might as well do it now while they came up on the screen and I had to think about what they were. So if you remember what happened, and I'll draw this on the blackboard because this is particularly important to understand, I suppose. And it's something that has a subtlety that we're probably going to have to deal with later in some way. Maybe with alpha to coverage or something like this. But so we have an issue here, which is that if you remember how our hero sprite was made, this was just, we still have never updated to real art yet. We're still just using mostly stand-in stuff. So what we did is we had a sprite that was, the ground shadow, and then we had another sprite that was the hero, torso or whatever, right? And then another one that was the head and whatever, right? Well, now that we're drawing with a Z buffer, remember this whole thing is getting set to a Z value of whatever its Z is into the depth buffer. So the depth buffer is writing whatever the Z value is of this sprite into the depth buffer at that point. What that means is when this sprite comes along and tries to draw, even though the ground shadow was only this small thing down at the bottom, this whole area got cleared out by the Z buffer, right? So when this tries to draw, it's like, nah, I'm at the same Z as this, and there's already something there I'm not going to draw, right? So there's two things we want to do to help with this situation, because it depends on the circumstance which one is going to make sense. There's actually three, but we're going to leave one of them for later because it's more of an advanced thing. So what we want to do here is say, like, oh, OK, well, if that's what we're going to do, we need to, first of all, probably stop our sprites from filling the Z buffer if there isn't any actual color information there. If the alpha value of the thing is 0, we shouldn't draw in. And there's a thing for this very, very purpose. which is GL alpha func. So what GL alpha func does is it says, all right, in addition to testing against the Z buffer to determine whether I should draw, I'm also going to test against the incoming alpha value. So if the incoming alpha value of my sprite doesn't meet a certain threshold, for example, which I can use by setting up the equation here, I'm not going to draw it. So what you can do is say, all right, I can set never, less than, equal, less than or equal to, greater than, not equal, greater than or equal to, or always, right? To specify how I would like to compare the alpha value coming from my sprite with this reference value that I supply, and if the function does not succeed that I specified, if it's not, say, less than the reference value, it won't work, right? So you can see here them defined. If I set it to GL never, then nothing will pass. It's always discarded, the fragment. If I set it to GL less, then it passes if the incoming alpha value is less than the reference value, right? So basically, this would give me something that the smaller the alpha value was, the more likely it was going to pass. But I don't want that. What I want is greater than, right? I want to say, or perhaps greater than or equal to. I want to pass in a reference value here that's something low, like 0.1, and say if the alpha value is not greater than that, then assume that there's no sprite at this location and you shouldn't draw, right? So that's step one. And I don't know what we want to set this to yet. We're going to have to talk about that a little bit later. Certainly, it has to be higher than 0. But I forgot one other thing. Well, I think I know this one by heart, so I guess I don't have to look at it. But this, much like the depth mask, is controlled by a Boolean enable. So when I set the function, I still need to turn it on, right, by specifying GL enable GL alpha test. Once I've turned on alpha test, then it will actually execute that thing. And now you can see we're starting to get a little bit better, right? Now you can see that we're properly sort of clipping those things to their regions. But you can see another problem or set of problems, and these are all problems we're going to have to deal with a little bit more carefully as we go. So you can see here that if you look in sort of the areas around the tree, for example, or around this piece here when it's actually visible, you can see that by clipping it to 0.1, we actually create two types of problems. And this will happen wherever we clip it to. If we clip it to too high of a value, you don't get any softness. You don't get the softness that you would expect. If we clip it to too low of a value, then we get, sort of a band area where the alpha isn't really high enough to warrant clipping, but it's still going to happen. And you can see, oh wait, that's not hot code reloadable. I should have made that reloadable, but I didn't. You can see that. Let's say we made it that it just has to be greater than 0, for example. And now you can really see where the problem is here, right? And the reason that that problem exists is just because we don't, at the moment, have any clean way of making sure that the draw order is proper in this case, right? Because those alpha values, and this is an inherent problem with the Z buffer, it's the one problem I think that we're really going to have with it that we have to be clever about how we're going to do it. But what happens is, if you imagine before why our alpha blending worked, if I have a tree and then I have something behind the tree, this whole area has alpha values in it, right? And those alpha values are important because they are telling me how much of the tree to blend with whatever's behind the tree. It's a way of getting subpixel information in there. It's like, here's how much of the tree was in that one pixel or something, right? And so in that case, what that means is we have to know what's behind it first before we can use what's in front of it. In this case, that becomes a big problem. because we don't know what order these things were drawn in. The whole point is we want to draw them in any old order. We don't want to have to think about it too much, right? So it's highly likely that rather than this being drawn first and this being drawn second, this may be drawn first and this will be drawn second. In that case, we're totally, there's nothing we can really do given the limited tools we have at the moment, because when this tree draws, it will set the Z buffer all along its entire line there, no matter what the alpha values were, as long as they were above 0. It'll set them to basically being at its Z value. This will come along and be at a deeper Z value, further away. It won't draw anything in there. So what we end up with is no blending, right? We get perfect blending if they happen to draw in the right order, because the Z buffer will correctly determine that this tree was in front of whatever was behind it. But if they happen to draw in the wrong order, just happenstance, then they still sort properly, because the Z buffer takes care of the sorting, but we don't get any blending, right? And that's a problem. So hopefully you can see why that causes a nasty problem, because again, we don't know what the sort order of these things are until the Z buffer takes care of it for us, and so we don't have any way of really reproducing that blend that we need to reproduce. So that's going to be something that we're going to have to deal with later. It's important. And this problem only gets worse with shadows. Shadows are supposed to be soft things that kind of have lots of low alpha values, and they're the worst, right? Because they're effectively a transparent object. So you can see that we're going to have to think a bit and do some cleverness with our rendering in order to get something that's that's reasonably workable there. And yeah, that's going to take some cleverness to avoid having to get back into the business of sorting everything again, which is exactly what we don't want to do. And so we do need to bring some cleverness there when we get to that point. Now, the other thing we need to do here is we need to set up a very similar to our alpha function. We need to talk about our depth function. So let's take a look at that function as well. It's basically the same kind of thing. Load that up. So you can see the GL depth func here. Now you'll notice that unlike alpha func, it doesn't take a reference value. Why? Because that value is coming from the depth buffer, right? In the alpha case, we're just setting a threshold. In the depth case, we're talking about how to compare against the depth buffer. Same set of options here. We can have it so that it never passes. We can say that it's got to be less than whatever the stored depth value is, right? And that's what we want in this case. If we wanted to draw things in order, however, what we really want is less than or equal to, right? We want to be able to say, hey, if the thing coming in happens to be the same as what was already there, draw it. Because we're probably going to want to do things where we send 3 things down, say, that are meant to go on top of each other, all at the same Z value, and we want a good chance of that working. So we probably want something like that. And now you can see we get back to sort of closer to what we had originally, because now that drawing order is getting respected, right? And so that's a good thing as well. So there we go. Now our Z buffer is functional. We are drawing through it. We're going to have to do some work regarding alpha testing, and we're going to have to think about that. Again, that's not really something that I've typically had to deal with when I've been working on game stuff, because I'm usually used to 3D things more. But this is a problem even in 3D things. You end up with the transparency problem that we talked about, where you have to sort your transparent objects and stuff like that. Obviously, for this game, we want to get out of the sorting business. We want to be able to throw a lot of things in here. We're going to have to find some clever solutions there. Maybe use alpha coverage or things like that. But we'll try to figure out some good solutions using the horsepower of the GPU, which we're not really utilizing in most other ways, right? Because we're a more simplistic 2D game. You know, we're going to have to start thinking about it and just figure out, okay, what's a good way that we can utilize the power of the GPU to get us some nice blending here without having to worry too much about sorting, right? So anyway, that's where we're at. And so now we just need to start to work on how we're going to stack those sprites up, because this flashing is still going to persist until we actually have something stable to be sorted. You can see when I kind of come through here, the problem that we have there, which is that we really just don't have any way for the z-buffer to differentiate between these. It's all stacked on top of each other, and the draw order determines when they draw. You can also see, due to this right here, you can see, I don't know if you can see that. As I rotate back and forth, you can see the trees kind of slice in and out. That is actually a classic case of z-fighting, right? I've got two things stacked on top of each other that happen to be at the exact same z-values the whole way, but because they are different actual triangles, right? Because one of them is, like, for example, this is two triangles here that make up a square. And this is like two triangles that are bigger, right, that don't coincide. They're not identical. Iterating the z-values across those triangles leads to slightly different results. And so they no longer are exactly equal, and you get, depending on where the iterators are, you can see the banding in how those iterators were iterating and where the precision was for the transform. You can see that happening with the z-fighting, right? So we've got one more thing we need to do. I guess now that I think about it, though, the z-fighting reminded me of this. Before we go any further with our z-buffer, which is that we're not properly processing z-values to give them good values for the z-buffer. Because remember, our projection matrix, we haven't looked at that yet. So we do want to do that. And in fact, that might improve that z-fighting there a little bit, but that's a separate issue. Because we don't really want that z-fighting in the first place, right? All right, so let's see. Where is our projection matrix? Here we go. So here's what we're calling our perspective projection. And let's go ahead and grab that out of the math. So here we are. So you can see here, here's our perspective projection. And what's happening right now is whatever the z value is that comes in is the z value that comes out. This is kind of useless, right? If you think about it, the reason it's kind of useless is because we know that OpenGL wants the z values that get produced from the depth buffer to be in a certain range. I think I would have thought it would have been -1 to 1, but it sounds like it's 0 to 1. I don't know if that's... I kind of want the OpenGL spec here. It's too bad docs.gl doesn't have glue perspective. Can't remember. I tried to grab a good one of these. But I don't remember which page had a good one. Here it is. So I don't remember what OpenGL wants in terms of the depth values, but I assume it wants it -1 to 1. Yeah. So like I said, I thought it was -1 to 1 everywhere, but I wasn't sure. And then, so I guess it is in fact -1 to 1 everywhere. And then just when it does the window, when it actually outputs those coordinates, they become between 0 and 1 after the fact. It sounds like, because right, if that wasn't the case. There we go. If that wasn't the case, then you wouldn't be clearing between 0 and 1, right? You'd be clearing between -1 and 1. And so I think that they did the math as if you were on the -1 to 1 cube, but in actuality they then turn around after it comes out of that and sort of fudge it back into a different range. Right. Okay. So anyway, you can kind of see here, this stuff is, you can ignore this stuff for the moment. But you can kind of see what has to be happening here. What they're doing is they're trying to map between the near and far clip planes. They're trying to map that range into the -1 to 1 range. And we, I think, really could probably choose which way we mapped it, whether it was -1 to 1, where -1 was the near clip plane and 1 was the far clip plane, or the other way around, right? We could do either or. But it would just, all that would do would change how our depth values were, what we would set our depth function to, right? If we mapped it so that -1 to 1, where 1 was the furthest thing away and -1 was the closest thing, then obviously we want our depth function to be less than. If we did it the other way around, we want our depth function to be greater than, right? So how we map our z in the perspective matrix would determine how we would have to test against it. So let's work out the math here, right? So what we want to do here is set a near and far clip plane. These are basically going to be in that camera diagram that we've sort of been drawing very often. They're going to be, if this is where I'm looking from, here's my little eye, looking at the world is out here, right? There's going to be some place where I cannot see anything on this side of it, right? Nothing out here is visible, anything on this side of this plane. And there's also going to be something out in the distance that's the far clip plane, and nothing out here, nothing to this side of it can be seen. And so it's creating sort of a boundary that looks like this. Only this region is visible, right? So in addition to sort of the boundaries that the screen creates in terms of the left, right, top, and bottom boundaries, there's these near and far boundaries, and those boundaries clip things in Z. Furthermore, they set up the range for our Z buffer, because these are all the values Z from -1 to 1 will only encompass just this range, right? That's the entirety of the range that it will encounter. And so what that means, again, is that when we do our Z buffer, the precision of the Z buffer, how precise it can be with its computations and comparisons, is entirely dependent upon how big this area is, right? However we map this space, the Z buffer has only the same amount of precision. No matter how big I make this, it has to still cover the entire range with the same quantities in Z, right? So it doesn't have any ability to increase, it can't just arbitrarily invent more precision somehow. If I want to make something bigger, it means that I'm losing precision throughout this volume if I make the volume bigger. Whereas if I make the volume smaller, I get more precise, because I have more distinct Z values per unit of Z, per distance in the world, basically. All right, so what I want to do here is I want to be able to prescribe the near and far clip planes in terms of distances from the camera, and then I want to convert the incoming values so that they lie between those two Z values, right? Now what we know about the Z values that are coming in, obviously, and you can see that here, is that those Z values coming in are sort of going the wrong direction as well, right? So the Z values coming in are going this way. They're coming out toward the camera. But OpenGL wants to think of them going away from the camera, is the more natural way that it was thinking about. That's why we had to negate our W parameter, right? So in order to think this through, what we have to do is say, all right, we've got a near and far clip plane. Our Z values are coming in. They're coming in this way. But the near and far clip planes are going to probably just be described as distances from the camera, so they're going to be positive, right? So the near clip plane's, at 0.4f or something, and the far clip plane's at like, 100.0f or something like this. I don't know what we'll actually set them to, right? But what that means is those are actually distances along the negative z direction. Does that make sense? So what we want to do here is say, well, okay, we've got these 2 points. Here's my near, here's my far, right? And I've got my incoming z. How do I map it so that this becomes -1 and this becomes 1, right? Which is what I said I wanted. Well, I know some equations, right? I know some things that I want to have happen, right? So essentially what I'm saying is I've got a function that I want to define that a z value kind of comes into, right? And whatever my z buffer value is comes out, right? So this produces that z buffer value that's supposed to be -1 to 1. I know that if I put in like whatever this function is going to be, I know some things about it. I know that if what I feed it is -n, right? So if I feed it this value right here, this point in the world, I know that I want that to be equal to -1, right? If that makes sense. Furthermore, I know that if I feed it f, I want that value to be 1, right? So I know 2 distinct points that it has to satisfy, which gives me a lot to work with. So now I just need to know what is the structure of this function going to be. Well, I know that as well, actually, right? Because I am completely constrained. I have no ability to do anything other than what the perspective matrix allows me to do. What that means is I can look at the perspective matrix, and again, remember the perspective matrix looks like this. Actually, I'm just going to put dots in instead of x's so you don't get confused thinking they're actual x. Okay. And we know that w is going to be 1 in this case. So if I look at what happens here, remember, I don't care what happens to my x coordinate in this case. We're not talking about x. These values all affect the x coordinate. We don't care about them. They're not involved. Same with these. These are determining the y. We don't care about them. They're not involved. We already worked out what those are, and they're done, right? So we don't care about that anymore. That's over. Here, we've got a line that deals with the z, right? And here we've got a line that deals with the w. Again, w we've already worked out, and it's working fine for us. We don't care. So the z is what we care about. Looking at the z, what are the values we can actually use? Well, we can't use anything that's proportional to x or y, because that has nothing to do with what we're trying to map here. So those values also don't matter, and we can't really use them. So all we end up with is these 2 parameters here. We have a times z plus b, right? And those are the 2 things we can feed into our matrix there, right? We can put 2 values in. What that means is we know that the function of this the structure of this function is f of z equals az plus b, right? Because that's all I can do. So now, what do I have? I have the structure of the function, f of z equals az plus b, and I have the 2 points that I know have to be true. Well, if I combine these together, this is an equation in 2 unknowns plus 2 values for that equation. That is exactly what I need, right? An equation with 2 unknowns and 2 values. Elementary high school math. In fact, it's junior high school math. Solve the equation. That's it. So here we go. I know I have az plus b, right? And I want to plug in this case, -n, let's say, right? We'll do f first. So I have af plus b equals -1. That's one equation. And then the other equation I have was the one for -n. That's -an plus b equals 1, right? Those are the 2 points that I've got. let's solve these equations for A and for B. In this case, I have, I'll solve this one first. So I've got AF plus B equals -1. I'm going to choose to solve, in this case, for B, let's say, because it's already isolated. So I'll do B equals -1 plus AF, right? Oops. Minus AF. There we go. I'm just moving the AF to the other side. So now we have a term for B. So now over here, I can go ahead and substitute that in to solve. So I have -AN, -1, -AF equals 1. Right? That's just substituting into this equation. And then I can start to pull out my values. I've got -A, which is what I want to solve for here, right? I've got -A on both of these, so that's N plus F. And then I can move my constant over to the other side, and that's just going to be +1, so that's going to be a 2 over here. So you can see how I did that. And now I just need to solve this equation for A. That's going to be A equals 2 over N plus F. And the negative here I also need to get rid of, so that comes over to the other side. Divide by -N plus F, so that comes over to the other side, right? So there's my value for A. If I want to look at what that becomes when I look at what it is for B, I can say B equals -1 minus 2F over N plus F, right? And hey, that's actually just already done for us. We don't really have to do anything else there because we have, the complete equation. So, you know, math is hard. Let's go shopping. This is exactly the kind of thing that I often make mistakes at when I'm moving things around. I wish computers just did this for you. And sometimes they do. You know, Mathematica is not bad at it, but it tends to produce, it doesn't produce things in a clean way a lot of times. It's just annoying. I still haven't found the like computer-assisted algebra product that I really want in my life. Someday I'll have to make it. But this is the process by which we would produce these values. So let's take a look if they make sense from what I said. Because we can do 3 things now that, you know, we to test this. One is I can put in -1 and verify that I get n out. I'm sorry. One is I can put in n and verify that I get -1 out. One is I can put in f and verify that I get 1 out. And the other is I could put in, you know, 0.5 n plus f and verify that the thing I get out is somewhere in between, right? That I should be able to get something that maps between those two, right? All right. So let's take a look. So let's assume that these are the simplest I can make them. I'm not sure. Let's see. Yeah, it looks like, yeah, I don't see much else. I mean, we could write it this way. We could write it this way and then say, okay, -2f n plus f minus n plus f over n plus f. And this is just me, you know, again, if you remember sort of your junior high math, if I want to add 2 fractions, I have to make them the same denominator first. That's all I was doing there. And so if you see what happens here, now I can combine them on the top. And my b becomes -2f minus n minus f over n plus f. And the reason that I did that was just because if you look at what happens there, I was looking at it, it looks like it becomes a little simpler because now up on top I've got multiple f's there. I can just do -3f minus n plus f, right? And off you go. So I believe I did that correctly, but again, this is the kind of math that I tend to mess up. You can kind of see that it's a little bit strange. And so I can make both of these in terms of f if I want to, just like that. I can also make them in terms of the n plus f. I don't know. I'd have to think about if there's any way to do that here. I don't think so, but again, that's just sort of my math badness. But yeah, so negative 3f plus n over n plus f is what that looks like. And it just feels like, am I sure I didn't make a mistake here? Let's double check. Let's double check. So all right, so what's our final equation? AZ plus B, what would it look like in this case? I now know what A and B are. So I'm basically saying like, okay, f of z, and here's my A and B. So I've got negative 2n plus f in this case, and then I've got negative 3f plus n. Here's my z. Negative 3f plus n over n plus f, like so. So here's my values. Let's go ahead and plug in into my z. Let's plug in n. What do I get? So in this case, I get negative 2z, right? Yeah, negative 2z over, I'm sorry, negative 2n over n plus f minus 3f plus n over n plus f. And let's see, if I combine these, f of n equals negative 2n minus 3f minus n over n plus f. Yeah, you can see I've got a sign bug. I could feel it. I feel like, and I feel like I have a sign bug, but maybe not. Oh, maybe not. Maybe I didn't. So negative 3n minus 3f over n plus f, right? And that's negative 3 n plus f over n plus f, right? And that's not what I wanted, right? So I definitely have a sign bug, because it should not have been that. All right, so let's take a look. And again, like I said, you can plug this into something like a Mathematica and have it do it for you for checking purposes, but plugging back in and checking is usually pretty good. Of course, I also don't know whether I made a mistake in the actual plugging in. That's the best part about not being someone who's very good at doing computation math. I have no idea why we still have to do this sort of thing, but what can you do? Anyway, negative an plus b, I want to make sure that that's actually correct. So f of negative n, oh, that's my problem. I did two stupid things. First of all, when I plugged in to check, I didn't put in negative n, but also when I did f, it was supposed to be negative f, right? I messed it up. I said that f was supposed to be negative, and I didn't make it negative. So this is incorrect, right? Yeah, that's just wrong. So my f of negative n was correct, but my f of negative f was wrong. That's why it didn't look right. I was like, this just doesn't look like it's coming out to be what I would expected. And that's why, because I set up my initial things wrong. So I did have a sign bug, just not necessarily where I thought it was. All right, let's try that one more time. So f of negative n, we want that to be negative 1. F of negative f is 1, right? That's what I actually want. It's weird to have f in both places here. We'll just ignore that, pretend that never happened. And let's give it one more go. So in this case, again, we've got negative 1. We've got negative n should produce negative 1. So that means that a times negative n plus b is negative 1. And similarly, excuse me, for plugging in negative f, it's negative af plus b equals 1. Did I have those right this time? Looks right. Hopefully it looks right. Off we go. So now solving again, same process. B in this case equals negative 1 plus an. Again, just moving the an to this side. And on this one, I got to plug in this b again. So I have negative af and then negative 1 plus an. So you can see that that's very critical, plus an there. And negative af this time, whereas before both were negative, right? Yeah. So I think that's probably the only difference. We'll find out in a second. And then hopefully this will flow through properly. All right, so then off we go. We've got our negative 1 coming over to the other side, and we've got these two terms combining, right? So off we go. We end up with an minus af, in this case, equals 2, right? That goes to the other side. That's a n minus f equals 2. Or a equals 2 over n minus f, right? Plugging back in, we get for our b value, negative 1. Here's our a value. So that's 2n over n minus f, right? And again, let's combine the terms there just to see what happens. We get a negative 1 over n minus f. Oops, sorry. We get a negative n minus f over n minus f plus 2n n minus f. That, if we combine these two terms, we get 2n minus n plus f, right, in this case, because the negative distributes here, all over n minus f. Then when we're done combining these, we just get n plus f on the top, right? 2n minus n is just n. N plus f over n minus f. There's our b value. There's our a value. And so our final equation for f of z is 2 over n minus f times z plus n plus f over n minus f. OK? Plugging in to check, if I want to take a look at what my function will be if I plug in negative n, let's see what I get. I get negative 2n over n minus f, right, because I'm plugging in negative n to here, plus n plus f over n minus f. When I combine these, you can see what I get. And I get n, well, I get minus n, right, because I got negative 2n here and I've just got an n there. So I get minus n plus f equals n minus, or over n minus f, right? Which did I do that correctly? I did do this correctly, yes. This is where it would be nice if the stream, if I actually looked at the stream, because I'm sure the stream chat could tell me. So it's f minus n over n minus f, I believe correctly. If I'm not mistaken, I'm not sure. Did I do that correctly? N minus n plus f. Plug in negative n for z. Very slow math day here today, if ever there was one. Negative 2n should be on top. I should be able to combine these because they're both over n minus f. Yes. I feel like this is correct everywhere. But you always do. Right? That all looks pretty clean. Am I missing something? This guy might still be wrong. Let me just double check him. It's n times f over n times f, which is still -1, which is correct. So that's 2n minus n plus f over n minus f, which is correct. And that's just n plus f over n minus f. That looks right to me. That looks right to me. However, we know that plugging in f of -n in this case should equal -1. But this doesn't look like it worked out the way that I would have expected. F minus n over n minus f. That is correct. So what I can do here is just say, well, okay. Sorry, I'm paranoid about this, so I want to make sure it's correct. I think that's all correct, and this looks like it'll work out correctly. So f minus n over n minus f. If I pull out a negative here, n minus f is the same as f minus n if I pull out a negative, right? So at that point, I end up with being able to cancel the terms in this case. So that ends up being a 1 over a -1, which, of course, is -1. So good on that. I got a little worried there because I didn't think that was, I don't know, it just didn't look familiar to me. But hey, it ended up being correct. And let's try same exact equation. But this time plugging in -f just to make sure. And so that's, again, 2. The z value here now is -f. So that's going to be -f n minus f plus n plus f over n minus f, right? And same thing. Going to do -2f plus n plus f over n minus f. And now we say, well, okay, that's -2f. That's going to be n minus f over n minus f, which is 1. So those are the two answers that we wanted. That's a good thing. And so I think we can go ahead and use this guy. So there's our equation. And so then we know what to put in our matrix. We need to put in that and that. And then we can start specifying near and far clip planes. So in here in our perspective projection, we have our n and our f. At some point, we may want to pass these in. For right now, I don't think we need to. We can just kind of be arbitrary with them for the moment because we don't have anything we need to actually do with them. So we'll wait until someone actually needs to specify those before we think about how we might want them to be passed in or other things like that. But we do know, again, what our value coming in here is, right? Here's our A and our B. Unfortunately, we already have our B, A and B, so let's do D and E in this case. And so our D value is 2 over n minus f. And our E value is n plus f over n minus f. So that should do our mapping for us properly, we hope. And you can actually see already, even though we don't really have any way of testing this explicitly, you can see how there's a lot finer grained z fighting because now we're mapping our z to a real correct range, right? We're taking a scene, an actual reasonable slice through the scene, and mapping that to the full precision of the z buffer, as opposed to before when it was just whatever the z buffer happened to be, which meant that it would be getting clamped between -1 and 1, so only like the broadest z values would actually be doing anything inside where we were. So you can kind of see that that actually did already give some effect to our sprites there, right? So let's do, we don't have much time left, so let's just want to do one more thing here. Let's take a look at how our sprites are being outputted here in the render group. And we have this sort of notion of upright sprites, but we're not actually using it at the moment when we actually push stuff on. And I don't actually know if that's, I don't think that's coming through anywhere. I could be wrong about that. Yeah, you can kind of see we're setting this upright transform, but we don't use it anywhere, right? But we do know when it's happening. And so when we're in here in our render group, let's see here. When we do a push bitmap call, so when we're doing this push bitmap call, you can actually imagine what we could start to do here. In addition to passing down, like for example, our x and y axis, if we wanted to, we can set our x and y axis to be something that is not flat, right? We can have the x and y axis be something that's like standing upright more, and start to take a look at how that would progress, right? So for example, one thing we could do is say, like, you know, if object transform upright, and this is not even remotely a good idea, but I'm just giving you what the idea is. We could add some height to the sprite in the case where the object is supposed to be an upright object, just so we can see the difference between the two of them, right? Oh, wait, are the x-axes or only v2s? All right, that's fine. So what we need to do here is say, oh, actually, these have to be fully 3D. And then here we can just say, oops. There we go. And now when we're actually using these, we can always just actually use them, right? Oh, wait, I don't have to do that. All right. So now when we're drawing these, hopefully you can see what I'm getting at here. This is already starting to sort of do the thing that I was talking about, right? And you can imagine doing this fairly with a relatively exaggerated height, something that's not at all what we would actually want the height to be. But you can start to see how this will work, right? Looking kind of at how these go. This is sort of the diagram that I was drawing before, right? Everything is kind of slightly sort of slanted at an angle there. And then, you know, when we're drawing these things, we're drawing them in a way that allows the Z buffer to actually properly overlap things. And you can start to see how that will work. Now, you can also see, just based on what you're looking at right now, you can also see why we have to start taking the camera into account, right? Because we don't really want our game's sprites to look like sheared, right? So when you take a look at what's happening here, when I add that, that 1 value in there, I'm shearing the sprite in a way that is not appropriate. And furthermore, you know, like let's say I'm looking directly top down on this thing, like so. So suppose we were playing the game like this. You can see how it really changes the sprite in a way that really shears it and makes it too squatty, for example, down here, or too tall, for example, down here. But what we can do is if we take the camera's location into account when we're generating the sprite information, we should be able to work around that, right? We should be able to figure out a way to make that do something more reasonable, okay? And so that's the next thing that we have to do. We only have about 10 minutes left here, so I think maybe it would be a bad time to start that. But hopefully I can sort of give you an idea of what I mean by that. So if you just look at this guy who happens to be centered on. If you imagine here the y-axis, again, getting that sort of z slant up to it, what I could also do there is say, well, what if we also elongate that, right? And hopefully what you can see here is that for any given sprite that I wanted, so for example, this sprite here, this is the one I was working on. For any given sprite, we can pick a modification to its axis that when you look at that sprite from a particular camera position, like the one I'm in right now, it appears as the correct sprite again, right? And similarly, I could even do that with one over here that appears very bent, right? All I would have to do is take that y-axis and shear it. Do you see how that works? Oops. So now you can see that even something that's off to an angle, right, to the camera, and down in the corner, it's completely perspectiving out and all that stuff. If I just had a way of computing the axes that I was going to use so that they corrected for the camera distortion, to the viewer, it appears that the stamp has just been stamped down like a regular sprite with no modification, but in reality, it's this heinously warped, really messed up tree. Like it's that one, right? I mean, look at that thing. But from here, from the original viewpoint, it looks correct. Right? So what we can choose to do, depending on how we need to end up making this work, what we can choose to do is just use, every time we send down a sprite, use the knowledge of where the camera actually is to bend the sprite to properly align with the screen in a way that makes it appear as if it's being stamped down, even though it's actually bent in 3D, which is all we really need to have happen. And that will get us back to proper rendering with z-buffer sorting. And then the only thing that we're going to have to do on top of that in order to really solve the problem is we're going to have to figure out a way to deal with our blendable things, right? Like our basically the edges of the sprites, like this sort of thing here. That's the only thing that we're really going to have to deal with separately, because that is a real big pain in the butt. But there'll be other things we can do for stuff like shadows. You'll see when we take a look at those. Hopefully there's some things we can do with stuff like shadows. There's some tricks we can pull with that that don't force us to sort in as complete a way as we were sorting before. So we can do some simple tricks there that might potentially work. And so we'll have to talk about those as a separate issue. All right, I'm going to go ahead and go to the Q&A. And tomorrow we'll work on that transform there. I'll pull it out for now. So let's go ahead and Q&A. Ratchet Freak, when adjusting the sprite like that, don't you need to interpolate the texture coordinates in screen space instead of clip space, the default? Yes, we can. Well, I guess here's what I'd say. We certainly have the option of doing so if we want to in OpenGL. When we switch to shaders, for example, you can pick how they're interpolated. Even in the fixed function pipeline, if you needed to, you could do it if you want to. You just have to have a texture matrix set up, I think. I don't know if there's any other way to do it. Yeah, I'm not sure. But at least in shaders, it's a trivial. It just all you have to do is just change the declaration of like one variable, and you can interpolate in screen space. So we should have the opportunity to do that just fine as well. So what is alpha to coverage? Any good references on that? So what alpha to coverage does is, and I don't even know, like I'll probably have to go do some reading myself to see if there's better modern techniques, because it's possible that that's not even really what you would do these days. That's old. That's an old technique. What alpha to coverage does is it says, well, all right, if you set up a multi-sample buffer, so if you basically set up anti-aliasing, like the kind you normally do in 3D, what you can do is say, oh, when you're actually drawing, instead of using the alpha channel as blending at the time, you can use the alpha channel to say how many samples in the multi-sample buffer you want it to fill. So that basically does it uses the anti-aliasing capabilities of the hardware rather than using alpha blending, so that you don't have to worry about the order anymore. It's a little less precise than alpha blending, but it's an interesting option, right? Would an orthogonal projection matrix be applicable for your game? It might be, but I don't think so. We're going to have to see. Now that we've taken the step to 3D, we have the option to kind of play with that a little bit. And I'm thinking we probably still want perspective. Because again, I want things to... I want multiple floors to work properly, and I also want some other things to work properly that we'll see as we go. Sherlock 93, is the negative n and negative f because OpenGL has the camera on the negative z-axis? Well, more specifically, the camera having negative z pointing away from us in x and y is sort of what we want. That's our math view of the world. So really, more specifically, the way to say it might be that the reason we have to do the negative a and negative f is because OpenGL wants to use the divide as a value that increases, because that's how the perspective divide has to actually work, right? And so because they chose not to bake a negative into the divide, the projection matrix has to do that negation. Magic 603, why are you using legacy OpenGL? We're using legacy OpenGL because I feel like that's the right OpenGL for people to learn first, in some sense. Because if you don't know legacy OpenGL yet, it's a lot harder to learn non-legacy OpenGL. So like, legacy OpenGL lets you pretty much just not set up anything and just start drawing, right? It's very easy to use. Non-legacy OpenGL is nuts, right? I mean, you got to do all sorts of stuff. You have to teach people what a shader is. You have to write shader main routines. You have to declare variables, set up vertex and pixel shaders, and all this stuff. And so it's really just, at least as long as OpenGL, as long as legacy OpenGL continues to be viable, it's much easier to show people how to use that first and then show them how to use shader-based OpenGL. And since none of it's low level anyway, like all of it is completely just telling drivers what to do, right? We never get to really do anything particularly low level. I don't see any real reason to skip the legacy pipeline, because that also was exactly how you programmed, say, an IRIX-GL machine. It was 100% low level at that point because it was mapped directly to the hardware, right? C Voucher, do you typically use an infinite far plane for increased precision? Sean McGrath mentioned it in his stream a while back. So here's what I'd say. I do often use an infinite far clip plane in 3D stuff. I wouldn't consider it appropriate for this because we know exactly where our end bound is. So I don't know that it's necessary for that. But unless I'm missing something, I don't know why you would characterize that as something that you use for increased precision. It's not really increasing the precision per se. It's increasing the view distance, if that makes sense. I guess I can see why you might consider it increasing the precision, because if you were talking about having to set the view plane out that far in practice, then you lose a lot of precision up front where you care about it. So I guess I can sort of see why that would be a way to say it. But in our game, everything's fairly, we don't have a large swath. It's pretty narrow. So I don't know that we would bother using an infinite far plane here. But I do use that oftentimes myself in 3D stuff that's not in 2D. Mesielda, would it be simpler to use orthographic transforms for upright objects? Are you not simply undoing the perspective projection there? So it would be simpler to use if we didn't care about mixing the two, right? But what I am suspecting is I want all of the perspective stuff. And I don't know that for sure, but I'm guessing that I really want all the perspective stuff. So what I would rather do is just fuss with the sprite coordinates for things that are standing upright so that they get mapped properly, rather than turn off perspective and have to deal with orthographic. That's my guess. In fact, I'm pretty much certain of it. Would it be possible to use a shader to do the Z-buffer rendering? I guess I don't know what that means, per se. Meaning, you may be asking a question. I don't know what question you're asking, I guess is what I would say first. So you may need to clarify it. But shaders can use the depth buffer just like anything else. So in a shader, you have the ability to do depth testing and whatever else you want. However, the shaders, the depth buffer is sort of handled specially, you might say. So depending on what you're doing, certain things you might want to do in the shader might be more or less costly, depending on how fancy you want to get. What I mean by that is depth testing has a special place in the shader. It's not generic. It's not 100% generic. While you can do 100% generic depth buffer testing by binding a texture that is the depth buffer and operating on it separately, there's a bunch of early out special condition stuff that the graphics card can do when it knows it's talking about its main primary depth buffer. And so in the shader in general, you can do anything you want in terms of depth testing and rejection and whatever else. But if you use it the way we are traditionally using it here, you may get a speed win. Whereas if you do arbitrary sorts of stuff with it, in terms of the complexity of how you use the information in the depth buffer versus what you're when you decide to kill or not kill a pixel, you might incur speed penalties because it can't use things like early Z outing on whole blocks and stuff like that, and like other sorts of compression tech that it has. To what degree that matters is, hand wavy and depends on the card and what you're doing and all that other sort of stuff. But, the general answer is shaders, you can set up the render path so that you can do pretty much anything you want in terms of calculating what you want to do with the depth buffer. So the near and far plane are linearly mapped. I've read somewhere the mapping is not linear, in which cases we do not make them linear. Yeah, I'm not sure I understand what you're saying there. I guess let me throw some things out there for you. Technically, with a perspective projection matrix or any other matrix, nothing can be nonlinear, right? And the reason we know that is because a matrix is a linear operation. So there is no way with just the matrix to do anything other than linearly map between the near and far clip planes. That said, we don't only have a matrix. We have a matrix plus the synthetic divide by W at the end, right? So what that means is we can, if we want to, use the synthetic divide to do a nonlinear mapping of the near and far clip plane range, but it can only be one that is still compatible with our Z divide. So we can put the Z that we were using excuse me. We can put the Z that we were using in our divide by W. We can put that into the denominator because we know that our Z value will be divided by Z at the end, right? And yeah. In fact, now I think about it, did we forget that? We may have made an error here. I have to think about that. I'm glad you just brought that up because I totally forgot that. Where is my perspective? So I actually totally forgot about this when we were making this. I did the mapping from -1 to 1. We did not factor in the divide by Z, however. Right? After this this runs, we have a synthetic divide by Z that happens here, right? Our -1 will put our Z actually into the denominator of these functions, right? Not saying this very well. So after we put these guys in here, right? So we've got so after we put these guys in here, right, we have AZ plus B here, but we also have -Z coming in here, which means that this actual quantity is going to be AZ plus B over -Z, right? There's a divide by -Z that implicitly happens here. And so technically, we should have accounted for the divide by -Z in our coefficients, right? Because we need that -Z to, we need to still map between -1 and 1. We want to have that mapping between -1 and 1 happen even after we divide by -Z, right? And that's where the nonlinearity comes in, if that makes sense. So actually, because we are doing the divide, if this came out to 1, so if we were doing an orthogonal matrix, then it wouldn't be the case. But if it comes out to negative z, which is what we're doing it here, then it will actually be nonlinear, because that is going to go into the denominator, right? And we can force it out of the denominator by sticking z in here separately, but yeah, because it's in there, what we should have done is compensate our two terms by that value, right? So what we want to do is say, well, this whole thing sort of has to be multiplied by z as well, right? If that makes sense. And so yeah, and so what we might say here is like, okay, so we've got our c, we've got cz plus d, let's say, and we want that to equal I guess we should say we have cz over z. And we want that to equal our az plus b, right? And so you can kind of see what happens here. If we end up with a cz plus d in this case, we end up with these coefficients being, because we're going to multiply both sides by negative z, we end up with a being negative z a z, right? And this is negative zb, right? In these cases. And so looking at what the terms have to be, you can see that this is not strictly possible because now these are both in terms of negative z. So we can't assign them to two variables, one that doesn't have z in it and one that does, right? So that becomes quite tricky, actually. However, I'm pretty sure, let me double check. So let's just see, because again, like this all depends on what OpenGL wants. Since it's not our code anymore, we just have to guess. Where is the glue? I never can get a good. So the only question I have, and I don't actually know, is just whether or not OpenGL expects that to be the case or not, right? Like, I just don't know whether it lets us do that divide first or not, or whether it wants to do that, if it does that divide first before taking the value for the z buffer or not. I guess at the risk of being incredibly dry, the easiest way to usually figure this out is to actually look and see what the spec says. It just takes a while, so I'm sorry to do it on stream. But that's usually the way that it's easiest for me to figure out what it is OpenGL does with the values and when. I think I want the transforms here is probably section. Let's see. Coordinate transforms. Guessing that's probably where it is. Let's see. The viewport transformation is determined by the viewport's width and height in pixels, px and py respectively, and its center, ox, oy, also in pixels. The vertex width coordinates x, y, and z are given by x, y, w. So ZD is, in fact, divided by W, right? You can see that here. So pretty sure the factor and offset applied to ZD encoded by N and F are set using the depth range. So that's fine. Excuse me. O and 1. That's where all arguments clamped. Okay. So there's that mapping to 0 to 1 that we suspected was there. It's there, and it happens within this range. Presumably, that's normally -1 and 1. So there we go. But yes, it is divided by that value. So technically, right, we're going to have to redo this guy. Because technically what ends up happening here is, if we take a look at this equation again, what we actually have is we have AZ plus B over negative Z is what we actually expect our f of z to be, right? In theory. So if we actually want f of negative n to equal our -1 and our f of negative f to equal 1, we actually need to do the math assuming this is the actual output value, right? At least I believe that's the case. We don't have time to do that right now, but I guess that's what we will have to take a look at. No, Sherlock, that's a very good question. I'm glad you said that, because we would have made that mistake, and it would have been a hard mistake to notice for a long time. Like, and I guess the other way to do it, too, here is we could also say it slightly differently. We could say, so if you plug in negative n, right? We want to be -1, but we know that we're going to divide by negative z. So actually, in this case, it's going to be -1 over negative z, right? Which would be just z. And similarly, in this case, we have a negative f. And so we know that this is going to be 1 over negative z, or just negative z, right? So what we actually want to have happen here is we want to have our AZ plus B. In this case, we want to do like negative n. We've got negative AN plus B. We want that to equal Z. Which is our incoming value, right? Which again, yeah, it's just going to make it harder for us to solve. It's going to make it harder for us to do the math out, but that's really all it is in this case. When we divide this guy by z, you end up with, I guess you could also look at what this ends up being, right? In this case, we just end up with z over negative z. So this is really just negative a, right? Because that divides out. And it's negative b over z. So you could just divide by z first, and you end up with this as your actual equation that you're trying to solve. That might be the easiest way to do it too. So if we take the negative n case, for example, equaling -1, we'd get -1 equals negative a, and then negative n's on the bottom, so it's plus b over n, right? And similarly, if I want to do the negative f version, we'd end up with 1 equals negative a plus b over f, right? And so then solving these guys, swap the a with the 1, and you'd get 1 plus b over n is your term for a, right? Just swap those two guys. So each one becomes plus. And then when we sub that in here, we'd get 1 equals negative 1 plus b over n plus b over f, right? Because in this case, we just have to swap this in here. Otherwise, everything else stays the same. And so there we end up with, when we do the subtraction in, we get negative 1 negative b over n plus b over f, like so. Excuse me. And the negative 1 comes out temporarily, let's say, to the side. Let's put that over here so we end up with a 2. And then this we have to add together. And so you can see the same thing would happen here. We'd end up having to cross the terms in order to make that work. So we would end up with b over f minus b over n. We need to solve, not solve, we need to be able to combine these. So we need to be able to multiply both by whichever one it doesn't have, right? We need to make these two denominators the same. So we need to put an n in here, so this would be bn fn, and we need to put an f in here, so we'd have bf nf, right? So then we're just left with b n minus f over fn, like so. And then we are able to solve for b, which is what we wanted, right? Our b is going to be 2fn over n minus f, right? That means our a value is computable now. It's understandable to us. It's just going to be, the b comes up in here, so we end up with a 2fn over n minus f, but that's, of course, the over goes down to the bottom, so it's actually n minus f, if that makes sense. And there's your a value as well. So then we have excuse me, two different values for those. I don't know if it's worth combining these terms. It might be. I could take a look. So 2fn plus n minus f over n minus f. That's just if I turn this into an n minus f over n minus f. I don't know if that does anything for me. At the moment, I can't say that it looks like it does. Yeah, I don't see anything in particular there. So that and that look like the most condensed forms that I would probably use. But let's just double check again like we normally were before. So if we rewrite this equation, so we've got f of z equals az plus b over negative z. And these are the two guys we're using here. If I write that out longhand, I just get 1 plus 2fn over n minus f times z plus 2fn over n minus f all over negative z, right? And so if I want to simplify that equation out a little bit, I can, excuse me, I guess ahead of time divide the negative z out here, and that would just be 2fn over zn minus f, right? Minus this, I guess I could write that, oops, minus 1 minus 2fn over n minus f. Right? And hey, you can sort of see that this probably checks out pretty well. If we wanted to plug in z equals negative n for our near clip plane, so we've got the z value right there. The negative n, if we plugged it in, would give us negative n minus f. That turns this whole term negative, which means these two cancel, and we just get minus 1, which is exactly what we want. So the only question is, does negative f work? And in that case, we would get 2fn. Actually, this becomes a plus. So 2fn over fn minus f minus 1 minus 2fn over n minus f, right? That's what we've actually got. And so in this case, if we actually want to combine all those terms, it's sort of a nightmare because we've got an f and an n on separate sides of this, right? And we have to figure out a way to get those guys together. So we're going to have to multiply both sides by, one of these two things would end up having to square itself at first, I believe. So let's see if that actually works. So if we have to introduce an n to this term, we'd end up with 2 fn squared over fn minus f. In fact, the whole thing can now be over that. Right? Sorry, fn. Minus fn n minus f, which is the one term, minus 2f squared n. Right? That's what we're actually going to get here. All over fn n minus f. And in this case, we're in reasonable shape here because the fn is actually already isolated and will cancel in all of our terms. So that's pretty easy. If we do that cancellation, we just get 2n minus n minus f, right? I'm just canceling this term here. Minus 2f over n minus f. If we look at what that becomes when I simplify this by pulling out the 2, I get negative n minus f. And then I'm going to pull out the 2. So plus 2 n minus f over n minus f. Right? I think that's correct. Yeah. And these guys would cancel, which would just give you negative 1 plus 2, which equals 1. So there we go. I said I wasn't going to do it because we were out of time, and then I did it anyway. What are you going to do? There we go. So here we've got our a value being 1 plus 2 times f times n. Divided by n times n minus f. Did I type that in right? And then here we've got 2 times f times n over n minus f. You can see there's common terms there as well, so you wouldn't actually have to compute all of those. And I think we've got all those. And so that should be correct now. Not at all. I did type that incorrectly, right? It's 2 times f times n over n times n minus f two times f times n over n minus f being e. I feel like that should be correct. I will leave it for next time because I don't want to try and find the bug in that math right now. Oh, and no, I don't know. I think I typed that in right, so I must have typed in the math wrong, or not typed in the math wrong. I must have gotten the math wrong. Because you can see we're working just fine, but when we change to that Z mapping, it is not correct. All right, so anyway, I'm going to end it there. We will pick up tomorrow and take a look at if we made a mistake math-wise or if there's something we were missing there. Oh, you know what? Wait a minute. Did I? No, that should be good. I don't know. Well, we'll take a look at this again. And we'll figure out what the problem is here. I like being able to zoom in and out on the math. It's funny. So we'll take a look at this again, and we'll figure out what the problem is here. We'll do that tomorrow. I would love to do it now, but I really have to go. So that'll be the end of it. So I apologize for leaving you hanging on that one. But since I don't immediately know what the problem is, I feel like it could be an arbitrarily long amount of time before I find it, and, you know, I got to end at some point. So thank you very much for joining me for an episode of Handmade Hero. It's been a pleasure coding with you as always. If you would like to follow along the series, you can always pre-order the game on handmadehero.org, and it comes with the source code. And also, we have a forum site you can go to if you want to ask questions, a Patreon if you want to support the video series, a schedule bot if you want to know when we're going to be live, and an episode guide if you want to catch up on old episodes. We'll be back tomorrow, same time, 10 o'clock, in order to take a look at what we messed up in that Z calculation. And then after we do that, we'll have to go make our sprites correct for the camera location properly. So those are the two things we have to do. Until then, have fun programming, and I'll see everyone on the internet. Take it easy, everybody.